Okay, so thanks very much, team and friends, for putting together the program. Super nice, and for the interest in intro to Swampland. So I think many of you are many of you are already familiar with many of the things I'm going to be talking about. So, in order to make things more interesting, please let's try to have like a bit of it's going to be a talk, but let's try to have it like a bit of a hybrid between talk and discussion, in the sense that if there's anything pertaining to the topics that I'm going to be covering that you want to ask and we can talk about all of us together, let's please do that. That's probably a good idea. Okay? All right, so let's get going. So it's going to be Ben and I are giving you intro to the Swampland. I'm going to be giving you the first part of it, which is introduction to the general Swampland idea and no global symmetries. Okay? So the Swampland idea, let me just go over this part real quick, right? Is basically is based on the observation that if you want to couple, if you want to have an Einsteinian theory of gravity coupled to an effective field theory, quantum field theory for the matter sector at low energies, there's non-trivial constraints on the matter effective field theory. And this is not what you would expect, for instance, from classical point of view, right? So at the classical level, for instance, if you want to couple something to gravity, you would just say, well, let me just write Einstein-Hilbert action. And then if you want to couple any matter sector, just write some effective field theory Lagrangian. And no matter what your quantum field theory is that you want to have as the matter sector, you can always couple to gravity. How do you do it? Well, you just put the square root of minus g in front, change all ordinary derivatives to covariant derivatives, and then you're done. Bam, this is coupled to gravity. And at the classical level, this is completely consistent. So classically, it is completely okay. Quantum mechanically, is not obvious. Why is it not obvious? Well, Einstein's theory is not normalizable, so who knows what's going on at the UV. But more to the point, part of the reason why it's not obvious is the equivalence principle. Okay? Classically, you can choose any EFT with any couplings that you like. You can couple it to gravity. Quantum mechanically, because of the equivalence principle, that means that the graviton couples to everything. You're going to have, for instance, you're going to have matter couplings like vertices. They're going to receive corrections also by graviton loops. So that's very standard. You know, it's just graviton loops that you would also consider an effective field theory anyway. But, you know, there may be more exotic stuff like black holes and the like. And so it is not clear a priori that whatever Lagrangian you put initially, you're going to be able to, you know, it could be that the quantum effects reveal some non-unitarity or some kind of inconsistency or another. Okay? So the picture that you're all familiar with, I'm going to put here, right, is that there's the big space of quantum field theories or effective field theories that you could couple to gravity. And then there's the subset of them which are okay with quantum gravity. And most of them, the picture is, most of them are not okay. They cannot arise as the low energy limit of a consistent quantum gravity. Yes, Jose? Right. Look, right. What I mean is that in quantum field theory, if I want to protect some sector, let's say I want to have a global symmetry, for instance, you know, I can basically say that if I want to protect some global symmetry, as long as I don't write operators that violate that, they're going to be generated by loops. So in quantum field theory, there's decoupling. You can want to have, you know, gauge group SUN with n arbitrarily large, which is one of the things that is not so easy to do with gravity. Just stack theory after theory, take a tensor product, you can get very large theories. In gravity, the special thing about gravity is because of the equivalence principle, there's one field that couples to everything. Okay? There's no way to have decoupled sectors. And that means everything talks to everything else. I didn't really mean anything more precise than that. Just motivational thinking. Any more points? Okay. So the picture is that if you're the space of all effective field theories that you can write down, should have written like this. Then there's a subset of those which are said to be in the landscape. and consistently coupled to quantum gravity. And then the rest of it, the vast majority, you say are in the Swampland. So an effective field theory in the Swampland is completely fine as an effective field theory, but you cannot couple it to gravity. And so the point of the Swampland program is to find out the consistency criteria, consistency conditions, that tell apart the landscape from the swampland. Okay? So there's been, by now, there's been a lot of activity on this, and there's several consistency conditions. Ben and I are going to focus on 3 of those, which are the no global symmetries conjecture, the weak gravity conjecture, and the distance conjecture. Now, why do we call these things conjectures? Okay? The reason we call them conjectures is that if you want to come up with general consistency conditions for effective theories to couple to gravity, it's very difficult to prove this in complete generality because we don't have a framework that allows you to prove things with generality in gravity. So the general statements that we make, out of an abundance of caution, we call them conjectures. You can prove them sometimes. I will give you for instance, I'm going to focus in the talk on this guy, no global symmetries. I will give you some proofs of them in particular contexts, like the ADS-CFT correspondence with some assumptions, but there's no general way to prove these things in quantum gravity. So why do we believe they're true? It's essentially 2 kinds of things. So the evidence or support for this, essentially 2 kinds of things. On one hand, we have heuristic arguments, or proofs in particular contexts. Okay? They're never fully general, but in particular contexts they work. And on the other hand, we have, for everything that we have here, we have tons of stringy evidence. For instance, believe there's no global symmetries in quantum gravity. You go and check in literally every string compactification that anybody has ever built, and you can always see that global symmetries are broken. So you use string theory in a sense as a theoretical laboratory. Even if we haven't found the standard model yet, it's still a good term. Yes, but not the standard model exactly, with the, you're right, not the real world, right? Like we haven't found with the, so in F theory, you can find the standard model with different forms on the global group, but we didn't find exactly with our Higgs potential, with the Yukawas, with everything that we have today. Modelized, stabilized, the sitter, right? But even if we haven't done that, it's still, everything that we have found so far can still be useful as a theoretical laboratory to check for these things. All right? So that's the general picture. I guess it's not new for most of you. So now let's get to no global symmetry. So I'm going to be spending the rest of the hour talking about the no global symmetries conjecture and its implications. To tell you what the no global symmetries conjecture is, first I need to tell you what is a global symmetry. Right? So what is a global symmetry? So to do that, I'd like to do it via an example. Consider the following reaction. Neutron goes to proton, plus minus. Okay. Does anybody know the name of that reaction? That's beta decay. That's a beta decay. And in this reaction, there's 2 conserved charges. Okay. So on one hand, electric charge is conserved, right? Because we have a neutron on the left and antiproton, electron on the right. So Q is 0 here, and electric charge is 0 here. But we also have another number, which is baryon number minus lepton number, which is also conserved. Okay, so on the left is 1 because of this guy. And here there's the antineutrino cancels one of the two, and then you still get 1. Okay, so there's 2 conserved charges here, but they are very different in nature. Okay, so electric charge is what we call local gauge charge. There's a charge under a gauge symmetry. And these are okay in quantum gravity. What does it mean that is a local gauge charge? In practice, what that means, this is the same as saying that the charge can be measured from far away. Okay? So if I give you a black box with some particles, I tell you there's some electric charge in there, and I ask you to tell me what's the value of the electric charge without opening the box, you can. You just compute the electric flux at infinity via Gauss's law, and you can tell me. Equivalently, another way of saying this, charge can be measured from far away. That means that the charge is 0 on a compact space. Right? Because if you're in a compact space and the charge can be measured from far away and I see no charge here, well, that means there's no charge anywhere. No net charge anyway. So charge that you can measure from far away, we believe is okay. With quantum gravity, that's a global charge. Sorry, that's a gauge charge. And then the B minus L, at least in the standard model, you cannot measure like this. I give you a black box and I tell you and I ask you to tell me how many neutrons are in there. There's no way to do that within the standard model other than opening the box and counting how many neutrons are there. That's a global charge. A global symmetry or global charge is some charge that you cannot measure from far away. There's no long-range gauge field that allows you to measure it from far away. And the way I presented it is, you're thinking of photons and stuff, like long-range gauge fields, but it applies also to discrete charges. Okay, so for instance, electric charge is valid on the integers, which is like saying that the electromagnetic group is U1, but this also works for Zn charges, for instance. You can measure, if I give you a box with a Zn gauge charge, you can measure it from far away by taking string and doing a Harnov bomb experiment. So that the phase of that will measure the charge for you, but you cannot do it for a global charge. Okay? So this is okay in quantum gravity. This is not. So that's the statement. I'm now going to give you like some justification for the statement, but before I do that, any questions about this? Any subtleties, any interesting edge cases that? That's right, in which case it's broken. It's very good, thanks. This is a good point. So in gut theories, right, B minus L, you embed as part of the SO10 or Patti-Salam or whatever. However, because you spontaneously break this gauge symmetry with the rest of the Higgs to the standard model gauge group, the selection rules of the symmetry are not obeyed in our vacuum. So for practical points of view, still, for instance, in Patti-Salam is broken, right? At the deep IR. It's a spontaneously broken gauge symmetry, which counts as broken. There's the other possibility, which is that it's actually gauge and unbroken. So if B minus L is a gauge symmetry which is unbroken, it has to be either broken and so if it's broken, you get things like you get standard model processes that violate B minus L. So for instance, you would expect things like proton decay or neutrinoless double beta decay. And the other possibility is that it's gauge and unbroken, in which case there's a fifth force. The gauge coupling of this force has to be tiny because we haven't measured it. So there's like some long-range force which will count the number of neutrons, for instance. Yes, yes. So the upper bound for this kind of thing, you can never fully exclude it, right? But it's almost excluded. So the gauge coupling of V minus L is less than 10 to the minus 25. If such a guy exists, it's very, very small, which actually is very interesting from Swampland point of view, right? Because if you try to go down this route, whenever you have a very small gauge coupling, you would also expect a tower of states from the distance conjecture. You can compute the mass of these guys, and it's not that heavy, so you get whole dark sectors and so forth. Okay? So there's interesting physics with that too. Sorry? So the Planck scale is 10 to the 19, so it's 10 to the minus 6 electron volts. Sorry, 10 to the minus 6 giga electron volts, so it's like 1 keV. Not really, because it's about the couplings that these guys have, right? How would you see them? Sure, there's this tower of guys, but they're coupled to the standard model so weakly. No. There's there's the species scale, for instance, which is much higher, couples to everything. The species scale is like G B minus 2 to the 1/3. This one is just the scale. There's some tower there. So in scenarios with large, like exactly, like a large extra dimension, if it couples very weakly, there's no reason to kill it. No, not because of this. For this reason, I think there's this paper by Matt. Well, not directly for the B minus L. There's a paper by Nathaniel Craig and Isabel Garcia where they try to actually use that to ameliorate electroweak hierarchy problem, for instance. So they want to say that the tower of weak gravity particles charged under these things are the neutrinos. That is actually okay with everything. And because the neutrino mass is coming from the Higgs, right? They try to argue that the naturalness problem that you get for the Higgs mass, the weak gravity for the B minus L relates to the masses of neutrinos, which are much more natural because they come from the Kawas and they only receive multiplicative correction. So that's one idea. So if you just take this, it's actually 3 orders of magnitude above the neutrino scale. So there's that window that would be okay. Right. Right. Assuming the tower and the tower couples to the for that dimension, you also need that is related to the vacuum energy. Like, yeah. Any more comments? Okay. So, okay. So I was going to tell you about what is the evidence for this no global symmetries conjecture. Okay. What do we believe is true? Okay. There's actually very old conjecture. Apparently, this the first. I think the first to propose someone like this was Wheeler, and there's a very old argument by Banks and Dixon, which is the following. Imagine, so let's try to, this is going to be a heuristic argument, this is going to be a full proof, but it's going to motivate why we believe this thing is true, and then I give you proofs in some particular context. So let's just go for the heuristic. Suppose you have a theory which has some global charge, let me call it B, some exactly conserved global charge. And let's say that in your effective field theory, the lowest particle charged under B, let's say there's a particle with charge B equals to 1, okay? And some mass M bigger than 0, strictly bigger than 0. So that's the lowest charge particle in the theory. Then you can do the following. You can take a cloud of n particles, okay? So the total charge is n, B is n, and you can collapse this to a black hole. Well, because these particles are charged in their global symmetries, there's no force between the particles, so you can just collapse it to a black hole. So B is equal to n. Okay? And well, because each particle has mass m, the mass of my cloud was m times n, so presumably this is also true of my black hole, right? It's bigger than this. Maybe to put them together, I throw some kinetic energy and so on and so forth. So the mass of the black hole is initially bigger than n times m. And then you let the black hole evaporate via Hawking radiation. So the black hole evaporates. When does it stop evaporating? Well, at some point the black hole becomes so small that it hits some cutoff, maybe the species scale, some other quantum gravity scale, and so it's so small that the Hawking calculation doesn't work anymore. But until then, the black hole is radiating, and you can actually prove, just follows from Hawking's calculation, that the average charge carried by the radiation vanishes. There can be very small fluctuations. You can take them into account. I'm just going to ignore them for this heuristic argument. So essentially, you end up with an object which is very small, right? The cutoff is maybe, let's say for simplicity that the cutoff is Planck. So you end up with an object whose mass is of order m Planck, or whatever the cutoff of the theory is. And the value of the charge is essentially unchanged. It's the same value of the charge that we started with. And so once you get to this point, you reach a conclusion, which is that if the m that I have is sufficiently large, in particular, if m times n is bigger than m Planck, then this object is kinematically stable, cannot decay. Because what would it decay to? It would have to decay to particles, and it would be a multi-particle state with charge m, so there's no way it can decay. Okay? So you end up to the conclusion that this state is completely stable. And I found one state which is stable and has mass 1m Planck, roughly. I could repeat this argument for n equals 1, 2, 3, 4, 5, for any n. So the conclusion of this argument is that you get actually many, strictly speaking, infinitely many stable states. Right? So that's problematic, and it's problematic because of this kind of thing. For instance, if you imagine that there's these little states which are called remnants, they do things like running in loops, etc., etc. They're probably very heavy particles. They give you very suppressed contributions to loops, but there's infinitely many of those. So they're going to completely overrun anything that you might have in the low energy effective field theory. Okay? And they're probably going to destroy the Einsteinian behavior of the theory at low energies. So if you have an exactly conserved global charge, you run into this kind of problem. We don't like that. But then it turns out that when you check in string theory examples, it never happens because there are no global symmetries in string theory. So that's a potential problem that you get out of by the fact that there's no global symmetries. So it's a heuristic argument for absence of global symmetries. Questions about this argument? Yes. Yes. That's interesting. I had never thought about that. That's interesting. Right, you're saying that, yeah, I completely agree. At some point, if I wanna, that's very right. I had never thought of that, but what Greg is pointing out is that this argument doesn't work in the zeta. because the first point is like I have this very large sparse cloud of particles, and in Minkowski you can have them and have them behind, not behind the horizon, but in the sitter, if you put too many of them, they're just going to fall into a black hole anyway. The other alternative is to put them behind the cosmological horizon, but then you can never bring them together. Yeah. So that's a loophole to this argument, which next time I talk about this, I will mention. Another loophole is, you know, the mass is bigger than 0. What if there's a massless particle which is charged on the B minus L? So, you know, the conclusion, if I was running this argument, the Minkowski would be no global symmetries or no massless particles charged in their global symmetry, which is not exactly what I want. Any more comments? Yes? Yeah. Well, right. So in a sense, that's what I was sort of like saying, right? Like you could say that you could consider the ensemble of all the possible remnants. So that's like a grand canonical ensemble, and that would have infinite entropy. Okay. There is a connection to the no-her theorem in the sense that the reason why you can get yourself into this pickle is because the average radiation coming out of the thing is 0. Okay, and that is the fact that the Hawking calculation tells you that the average charge being emitted is 0 has to do with the fact that global charge don't source any kind of hair. Okay, if you try to repeat this argument for a gauge charge, okay, you might ask, where does it fail? This is where it fails. In a Reissner-Nordström geometry, there's a non-zero electric charge. Like the black hole, of course, likes to discharge, right? And so you cannot get into this kind of problem. So it's related to that. Okay. Okay. Good. So we have this thingy. So there's no global symmetries argument. Let's try to do something more solid. I told you, I have either heuristic general arguments or more solid stuff in particular contexts. So I'm going to give you one such thing. Let's go to ADS CFT. In the context of the ADS CFT correspondence and with a couple extra assumptions, you can essentially prove this thing. Prove there's no global symmetries. Let's just do it for a simple case of a U1 symmetry. But what that means is that the charges are valid of the integers, valid charge. Okay, so let's try to do the argument for that. So ADS CFT tells me, so let's first suppose that we have some theory which has a exact U1 symmetry. And then let's see how this symmetry has to be gauged. So it's okay with quantum gravity. Comes out on the ADS CFT correspondence. So if you have a quantum gravity in ADS which has a U1 symmetry, by assumption of the ADS CFT correspondence, that means that in the CFT, there's also the U1 symmetry. And now, so if you have a symmetry in a CFT, CFT is a conformal field theory. So if you have a U1 symmetry, and you invoke Noether's theorem, you're going to land in the fact that your symmetry is accompanied of a current. Okay, I've just used Noether's theorem. And the usual prescription in ADS-CFT is that if you want to compute things in the bulk, to each field in the bulk is dual to an operator in the dual field theory and vice versa. And the dual field to a current is actually a gauge field. And you can prove it's the gauge field that sources the current. So just from ADS-CFT, just from holography and Noether's theorem, we get that there's a gauge field in the bulk for the symmetry, so the symmetry is gauged. Yes? So for the CFT, it means there's a conserved current. No. So a global, very good, thanks. The correspondence, this is like standard CFT studies, like a gauge symmetry in the bulk is dual to a global symmetry in the CFT, in the back. Okay? If you have a gauge symmetry in the CFT, that actually, there's no, it's because these gauge symmetries you could pretend are like redundancies. For instance, if you put it in a compact space, they're just redundancies, so there's nothing to see in the bulk. Okay? So we have this thing. So it looks like a very solid, very general proof, right? But I cheated a little bit. Can anybody see where I cheated? Well, I cheated even sociologically. I use your brains to cheat because I told you use Noether's theorem. But Noether's theorem is in fact not a theorem. Okay? Noether proved that whenever you have a Lagrangian theory, let's say with a U1 symmetry, you get a current. She didn't prove in general that whenever you have a U1 symmetry, you have a current. And she didn't prove it because in fact it's not true. For instance, take your favorite holographic pair, like n equals 4 Supergiant Mills. You know, there's a BPS sector, there's BPS black holes, and as you know very well, they are degenerate. The typical thing for BPS sectors is that there's more than one state with the same charges. So let's say that we are looking at, for instance, BPS sector of, at some BPS sector with some energy, and let's say there's K degenerate BPS states. What is a symmetry? A symmetry is something that commutes with the Hamiltonian. So just from this, you would say, and you were, if you remember the undergrad, you were using this all the time to solve the hydrogen atom and stuff. There's a UK exact symmetry that rotates every state to every other. They're degenerate. Yeah. So that means that there's a unitary operator, it's a finite dimensional Hilbert space, it's an eigenspace of the Hamiltonian. So I can define any unitary operator that just keeps you there, commutes with the Hamiltonian. Sorry, what? Yes, sorry. I was in n equals 4 Supergiant Mills. N equals 4 Supergiant Mills. To be very precise, let's say I quantize it on the 3 sphere. Okay? So that there's a Hamiltonian. So we don't have UK for K a million in equals Supergiant Mills. So what's going on? Well, what's going on is that Noether's theorem is not a theorem. Noether's theorem is a theorem for Lagrangian theories, and we believe it's true. Okay, there's a belief. It's true for symmetries that map local operators to local operators. This is certainly true for any Lagrangian symmetry. If you think, for instance, of a complex scalar field, phi of x, a typical U1 symmetry would do something like this. It's mapping a local operator at x to a local operator at x. Okay? A symmetry like this actually is very non-local. How do you see it's non-local? Well, this is a symmetry that only acts, for instance, on the in a particular eigenspace of the Hamiltonian. So imagine you take two operators by state operator mapping, which are dual to two states here, phi1 and phi2. If the symmetry was local, it would act on any state which is in the OP of these two guys in a way given by the product of representations. But the states in the OP of these two guys are generically not, so the sum of operators OI, which are not on this BPS state subspace. So the symmetry doesn't act on them. Okay? So this symmetry is, the thing is that we believe this is true for symmetries which map local operators to local operators. Yes? Yes. Yeah, absolutely. I'm just saying that the ones that, that you act in the Lagrangian like this, the ones that you obviously see in the Lagrangian. So for those are the ones for which we see the correspondence. The other ones are gauged in the sense that you can measure the charge from far away, but there's no simple way you can see it in the effective field theory. So what seems to be true is that in ADS, symmetries you can see in the effective field theory, you can actually show that a symmetry that acts on the effective field theory in ADS, almost by construction, is going to map local operators to local operators in the bulk, and by pushing those operators to the boundary, it's going to map local operators to local operators in the CFT. So this follows for any symmetry that acts on the effective field theory. Beyond the effective field theory, it could be weird stuff. But with those caveats, or with these restrictions, this is indeed a proof of no global symmetries in ADS-CFT. Yes, it's also, but it's a matter of definition, right? Somebody could come, condensed matter physicists might come and say, what do you mean? Quantum info people, you tell them this is not a symmetry, and look at you like you're crazy. So I think, but I agree with you. It's important, this is part of the definition that we usually use in quantum field theory, but we are not solving the problem by definition. It's just that any global symmetry in the effective field theory automatically is of this form. Okay? Yeah, this is not something I usually talk about, but since you guys already probably, I didn't want to make you too bored, so I wanted to mention it. And now I'm way over time. So that's what I get. Very good. So now quickly, more arguments for no global symmetries. You can see proofs in perturbative string theory. It's essentially the same proof. You can construct a vertex operator coming from a current, blah, blah, blah. And you can actually read this one in Polchinski's textbook. So that's one. There's a recent set of proofs. I'm going to put it under quotes. Even in flat space, using the gravitational path integral. So there's been this important realization in our field over the past 5-6 years that if you follow the rules of the gravitational path integral carefully, what you compute is averages of quantities, but you can recover very meaningful results that you think are true, like for instance, Yes, but also with inclusions of wormholes. So the idea is that what you need to do for, okay, let me, there's basically a generalization of the traditional Euclidean gravity path integral techniques, where you actually allow for any sort of like wormhole saddles if you have different boundaries, and when you try to compute things like entanglement entropies using the replica trick, which forces you to have several boundaries, things like the Page curve come out right, and it's very nice. And following that same logic, okay, there were some papers in 2020 by, for instance, one paper involving Luca Iliesu and Semin Yang, and the other involving Henry Lin. They showed that the same calculation tells you that the global symmetries are lost in the process of black hole evaporation. So I put it under quotes because, nobody, yeah, sorry. What they prove is that if you start with a global symmetry, then the selection rules of that symmetry are violated. And they can also show that those effects are absent if the symmetry is coupled to a gauge field. Yeah, so I put it under quotes because the gravitational path integral formalism nobody has derived. It's like magic, right? I mean, but this doesn't really have to do that much with the recent developments. The fact that you can compute the black hole entropy just by computing the Euclidean action of some saddle is a bit black magic, no? And so by taking those rules seriously, you can get to these conclusions, but the rules themselves are not proven. So, but I think it's very interesting. Another thing pointing towards the same conclusion. Any questions about this? Okay. So yeah, no global symmetries. It's very cool. There's many proofs, but it's not that cool really, because I told you here. I lied to you a little bit because I told you, for instance, for B minus L, you're either going to get a fifth force. But Mijan was asking, okay, what is the gauge coupling? I don't know. No global symmetries tells you that the symmetry is broken or gauge. If it's gauge, doesn't tell you how small the gauge coupling is. If it's broken, doesn't tell you at which scale the operators are appearing. So that makes it very weak. Like if you go tell your experimentalist friend, oh, the symmetry has to be broken, they tell you, oh, which scale? You say, I don't know, maybe the operators are suppressed by this. Then they don't care. So what I will tell you about in the next 15 minutes, briefly, is that, there's two ways to go around this difficulty. One of them, which we were discussing yesterday in the discussion, is try to quantify, try to do a bit better. If the symmetry is broken, try to quantify how bad it's broken. So we're discussing that it seems to be like it's controlled by the black hole entropy of the smallest black hole effective field theory, whose radius is given by the cutoff for the breaking case. Or you could try to quantify how small the gauging has to be, or if it's related to other things like the distance conjecture or the conjecture. But another thing that one can do, okay, is to extend no global symmetries to other symmetries, like p-form symmetries. Okay? By doing this, you can access different, the conjecture can actually become a lot stronger. So for instance, what is a higher form symmetry? For instance, for the case of a one form symmetry, we are used to symmetries having local operators being charged under them. So I was drawing before, maybe you can see it up there. Yeah, you see the charged local operator. This is multiplied by a phase. So that's a local point operator charged under the symmetry. But you can also have symmetries where things other than local operators are charged. So for instance, in gauge theory, you can have things Wilson line. Okay? So for instance, in pure Maxwell theory, there's operators like this you can write down, Wilson lines, you integrate on some line. And they behave like ordinary symmetries in many ways. So for instance, there's a conserved current associated to them. For ordinary symmetry, the current is a one form. For this guy, the current is a two form. But just like for ordinary symmetries, you might want to say that these guys are broken or gauged. In the case of one form symmetries, breaking the symmetry is the same as saying that the line operators that are charged under the symmetry can break. Okay? Why is that? Well, if you have, a one form symmetry is something in which there's some operator which is inserted on some line, and it's conserved. The symmetry is sort of conserved, meaning that you can deform the line, but you cannot. There's some charge that will prevent you from completely taking this away. If the line operator, if there's local operators on which the line can end, then you can always make, you can always shrink this to a point like this. In general situations, this could be linked to something else, so you cannot really open it without breaking the operator. So line operators can break, and for instance, for a Wilson line, the operators that appear at the endpoints, they are charged under the gauge group. Okay? So what I'm just saying is that this Wilson line, why is Wilson line gauge invariant? Wilson line is gauge invariant because if you do a gauge transformation, under a gauge transformation, this goes to, right? And this is the same as this. And if the loop is closed, this integral is 0. So the loop is gauge invariant. If I now declare that I want to have configurations where the Wilson loop can open, then the Wilson loop itself is no longer gauge invariant because the integral of d lambda on an open line, okay, is lambda at the at the m.2 minus lambda at m.1, which is not gauge invariant. However, the way to make this gauge invariant is to add some charge operator, so you can have some sort of like charge local operator, which transforms like e to the lambda 1 located at x1, o to x2, to lambda 2, o x1, o x2. You can stack this to the other, and you make a gauge invariant operator. So breaking one-form symmetries means the line operators can break, and that forces you to introduce charge operators. So breaking of one-form symmetries predicts that you should have in your theory of gravity, you should have all possible, all possible charges. All possible charges on the spectrum. So that's called the completeness principle. It's a consequence of no global symmetries. So for instance, by following this logic, you can predict that since we have a U1 gauge field in our universe, we should have magnetic monopoles. Okay, so that's one possible charge. And I didn't show the details, but it's actually related to the existence of a certain one-form symmetry in Maxwell's theory. So it predicts the existence of monopoles. Okay? So you can use it to predict new physically charged particles, which is interesting. Any questions about this? It was a bit quick, but I wanted to get to the like 10-15 minutes of cover this. Yes? Yes. Yeah, so the reason why this one is more interesting is not so much for experimentalists, because as you're saying, the mass of the monopole could be arbitrary scale. The thing is that this one, I'm not sure I'm gonna have time to discuss this in any detail, but when you impose absence of higher form symmetries, in theories, you know, you combine that with supersymmetry, it actually gives you constraints of the Lagrange effective field theory. The basic mechanism is very simple, is that, you know, I just predicted the existence of an electrically charged particle. If I do this for 2-form, 3-form symmetries, I'm gonna predict the existence of strings, membranes, right? And it turns out that these guys, they can have, you know, it can sometimes happen if you start with an effective field theory, which is in the Swampland, the work volumes of these objects can have anomalies, okay? And so that's an inconsistency. So you can run into an inconsistency when you say, well, completeness principle tells me I should have this or that object. But there's an anomaly in the object, so the object is inconsistent. So the only way out is to put the theory in the Swampland. The technicalities of how to make that more precise it require a bit of supersymmetry. So it's only interesting for supersymmetric theory so far. But there's been lots of work on this, you know, like the brain probes by Shiu, by Gary and Kumrum and Hitchell King. Also the papers in 8 dimensions by Miriam and the Penn group. So they all use this idea. So in that sense, that's more powerful. That's the key point. Like extended objects can have inconsistencies in their work volume, and that turns out to be very helpful. Yeah, so that's something that is very helpful for these kind of things. And I guess you can guess by now that the idea of this no global symmetries conjecture is always try to find an effective field theory, find that it has some sort of global symmetry, and then you can use, you can try to break or gauge that global symmetry, and that gives you constraints, okay? So any way to produce new symmetries is very helpful. And just to finish, I'm gonna give you one way of constructing global charges out of space-time topology. Which is what's going to motivate this covariance conjecture. Okay, so the idea is that any kind of way to get your global charge is going to be helpful because you're going to be able to either break it or gauge it. So let's construct global charges out of space-time topology. To do that, let's imagine we have a 5D theory of gravity. Okay, so 5-dimensional theory of gravity. And let's look at the constant time slice. Okay. So let's agree. Let's suppose that actually in gravity there's the topology is a dynamical object that can fluctuate and so on and so forth. And so in particular, I'm allowed to choose different topologies for my initial time slice. So in particular, one thing I can do, I can take instead of the flat space, I can take the flat space and glue some manifold, let's say a K3 manifold. Okay? How does this look like? Well, if you're away from this region, the metric is asymptotically flat. Okay? So this looks like I just added some sort of particle to the flat space geometry. And, in general relativity, topology cannot change. Like when you start solving Einstein's equations, the metric will change, but the topology won't change. So the topology of this guy is in some sense a conserved quantity. And for instance, you can compute topological invariance and depend on the metric like this. This is a number, which is conserved in dynamical evolution. So this seems like a global charge that you construct out of space-time topology. It's a global charge. Okay, and so you might want to break it or gauge it in a consistent quantum theory of gravity. But even though you might want to break it or gauge it in any theory of gravity, you should be consistent with, yes, Björn? Yes, but that's no different from me telling you there's a global symmetry like the B I was talking about before and throwing it into a black hole. So, yeah, but you're right. I mean, then you're asking, once it gets inside the horizon, it's not so clear that it's conserved or not. Precisely my point. Okay. But there's something else on top of this, which is, if I want to say that this topology thing is conserved charge, I have to be consistent with the same set of rules that I set for myself, no? If I started motivating that I can glue this thing because this topology changed in quantum gravity, well, maybe semi-classical is a symmetry, but there's some quantum effect that will kill it, right? So what we need to look for if we want to find a global charge is the set of non-trivial topologies, but taking into account topology change with smooth structure. So how do we quantify that? Well, imagine you have my manifold is like K3, and let me say that I'm considering the possibility that maybe has a transition to some other manifold M4, which possibly different topology. Okay? The things that you can describe in the effective field theory coupled to topology change, so the rules is I'm still doing Einsteinian gravity but allowing for topology change, is that, well, in between these two, maybe, there's some non-trivial topology here and the things change. So some handles here reconnect in certain ways so that you start with this manifold and you become this very different manifold, okay? So if I allow for topology change, and I want to say that I get new global charges by gluing topology like this, I should count this guy and this guy as having the same global charges because they are related by a topology change in transition. Okay? So my actual new conserved charge is the set of equivalence classes of manifolds which are related through this sort of like topological transition when here I can put any manifold. So here is 4-dimensional, so here's a 5-dimensional manifold, so let me call it X5. So this picture, like so I'm led to ask the question, which sets of manifolds are related in this way? Mathematically, which sets of manifolds are together the boundary of one manifold in one dimension more? And this is a question that has been asked by mathematicians. This equivalence relation is called cobordism. You say that two manifolds are cobordant if the two of them together are the boundary of one manifold in one dimension more. And so the set of conserved charges with this topology changing story in gravity is the set of cobordism classes of d-dimensional manifolds. So in this case, for instance, it will be 4-dimensional manifolds because it started in 5 dimensions, but you could do this in a number of dimensions. And the, let me see, I need to erase a little bit. Yes. Very good. Let me do it, for instance, for this case, for the particular example of the K3. Okay. So, suppose I tell you I have a particle with this charge and there's a gauge symmetry. One particular thing, as we were discussing, that implies is that if you're in a compact space, the thing is inconsistent because it violates Gauss's law. So one way to diagnose that the symmetry is gauged is that this comes from Maxwell's equations, right? Of f is equal to integral of j, so the integral of this has to be 0 because it's an exact form. An example of a theory where this charge is gauged is heterotic string theory. In heterotic string theory, you have the Bianchi identity, which is exactly analogous to this. You cannot compactify on K3 in heterotic string theory. Of course, heterotic string theory also has this other piece, which tells you that the K3 by itself is not okay, the K3 with a gauge bundle is okay. Okay? But that's another story. And since you ask about this, so in heterotic string theory, this charge is gauged. A theory where it's actually broken, for instance, is type 2A string theory. Type 2A string theory can absolutely compactify on K3. We do it every day, there's no problem. And the fact that the symmetry is broken, if you think about it, what does it mean that the symmetry is broken, for instance, for a point-like charge? For a point-like charge, you have the word line of the particle, and if the symmetry is broken, then the particle can disappear. That's what it means. So what that means is that if you have a configuration with the particle, the configuration admits a boundary. Okay? So the prediction of this is that in type 2, because the symmetry is not gauged, there should be a boundary compactification for type 2A on K3. In other words, there should be some sort of configuration which is like type 2A on K3 times, let's say, R5 times R plus, like half a line. And such a thing exists because in type 2A you have O8s. O8 minus plus it brains is something you can put as a boundary for type 2A. Yes? What do you mean the topology of the K3 can change? This is a solution. This is the solution you can write down. Yeah, it could be more complicated. Yeah, absolutely. Yeah, well, you typically, in this kind of things, you just ignore the non-compact part because changing it would have infinite energy. You could change it to anything else that you like. If you change it to a compact manifold, you should be talking about the 10-dimensional cobordism or 9-dimensional cobordism. So the thing is that this set of equivalence classes, it actually forms a group. I think I'll leave it there. I just told you briefly what it's good for. Sorry, I went slower than expected. So this set of equivalence classes of manifolds, M1 is equivalent to M2. If M1, where M2 is the boundary of some manifold, is called cobordism. And the set of equivalence classes actually is an abelian group, has an abelian group law. So for instance, if you have covariance class of some manifold A plus covariance class of some manifold B. This is how the abelian group law goes. It's very simple. It's the covariance class of A and B together. If you don't like having more than one connected component, you can join the two manifolds with a little tube, and it's still in the same covariance class. So this is actually a group law. It's manifestly abelian. So the covariance classes, they automatically form an abelian group called the covariance groups. Okay? And so covariance groups, or any effective field theory coupled to gravity in which you allow topology change, they furnish a set of global symmetries. And there's been a lot of progress on this in the recent years. People have been trying to compute these Bordesian groups for different string theories, heterotic, type 2A, type 2B, and chasing what happens to the different symmetries. Some of them are gauged, some of them are broken. In particular, in the cases where they're broken, you can use these kind of things to predict new branes. Okay, so this has been used to predict new branes in heterotic string theory and type 2. There's lots of work going on these things right now. So I'm out of time. Perhaps the beginning was a bit slow, but the point is that even this old conjecture of no global symmetries, I think still has a lot to give. One needs to think about extended objects for it to be more interesting. But there's lots of open questions, like what's the minimum amount of breaking? How far can you push these things? Are there more ways to construct global symmetry in effective field theories that could give you even more brains? So, I mean, I usually end up these kind of talks with like an uplifting message, like come join us, but half of you are working on this anyway. So I guess I'll just stop here and just keep up the good work.